Arithmetic operation with significant figures. Addition and subtraction. In addition and subtraction, the final result should be retained as many decimal places as there are in the number with the smallest number of decimal places. Example: 3.1 plus 1.780 plus 2.046 equal to 6.926. Here the least number of significant digit after the decimal is 1, hence the result will be 6.9. And 12.637 minus 2.42 is equal to 10.217. Here the least number of significant digits after the decimal is 2, hence the result is 10.22. Multiplication and division. In multiplication or division, the final result should be retained as many significant figures as there are in the original number with smallest number of significant figures. For example, 1.21 into 36.72 is equal to 44.4312 is equal to 44.4. Here the least number of significant digits in the measured value is 3. Then hence the result when rounded off the 3 significant digit is 44.4. Then example 2, 36.72 is divided with 1.2, then we get 30.6. Here 31 is the value because here the least number of significant digit is measured value is 2. Hence the result when rounded off to significant digits become 31. Dimensional analysis. Dimension of physical quantities. In mechanics, we deal with the physical quantities like mass, time, length, velocity, acceleration, etc., which can be expressed in terms of 3 independent base quantities such as m, l and t. So the dimension of physical quantities can be defined as any physical quantities which is expressed in terms of base quantities whose exponent power represents the dimension of the physical quantity. The notation used to denote the dimension of physical quantity is physical quantity within square bracket. Length m naught L T naught is equal to L. Similarly, area is equal to m naught L2 T naught is equal to L2. Similarly, volume m naught L3 T naught is equal to L3. Note that in all the cases the base quantity L is same but exponent power are different, which means dimensions are different. For a pure number, exponent of base quantity is 0. For example, consider the number 2 which has no dimension and can be expressed as 2 is equal to m naught L naught T naught dimensionless. Let us write down the dimension of a few more physical quantities. Speed s equal to distance by time taken. Here the dimension for distance is L and time taken for T, capital T. So here speed is equal to L T power minus 1 as like the velocity V vector is equal to displacement by time taken. Also V vector is equal to L by T is equal to L T minus 1. Note that speed is scalar quantity and velocity is a vector quantity. Scalar and vector will be discussed in unit 2, but both of them have the same dimensional formula. Acceleration A vector is equal to velocity by time taken is equal to A vector is equal to LT minus 1 by T. So we get LT minus 2. Acceleration is a velocity per time. Linear momentum or momentum is P vector is equal to mv vector. It gives P vector is equal to ml T power minus 1 as like the force F is equal to ma vector. So F is equal to ml T power minus 2 is equal to momentum by time. This is true for any kind of force. There are only 4 types of forces taken that exist in nature: Y strong force, electromagnetic force, weak force and gravitational force. Further, frictional force, centripetal force, centrifugal force all have the dimension ml T power minus 2. Impulse I vector is equal to F vector into T gives I vector is equal to ml T power minus 1. Angular momentum is the momentum of linear momentum is will later discussed in unit 5. Angular momentum L vector is equal to R vector cross P vector gives L vector is equal to ml power 2 T power minus 1. Work done W is equal to F dot D vector. Here we write the dimensional formula for F dot D as ml power 2 t power minus 2. Kinetic energy is of mv square. Also we can write as 1 by 2 into m into v square. Since number 1 by 2 is dimensionless, the dimension of kinetic energy k is equal to m into v square is equal to ml power 2 t power minus 2. Similarly, to get the dimension of potential energy, let us consider the gravitational potential energy. P is equal to mgh. Here we can write the value for mgh, where m is the mass of the particle, g is the acceleration due to gravity, and h is the height of the ground level. Hence, P is equal to mgh, and the dimensional formula for mgh is ml power 2 t power minus 2. Thus, for any kind of energy such as for internal energy, total energy, etc., the dimension is ml power 2 t power minus 2. The momentum of force is now as torque. Tau vector is equal to r vector into f vector is equal to tau vector is equal to ml power 2 t power minus 2. Read the symbol tau as tau, Greek alphabet. Note that the dimension of torque and dimension of energy are identical, but they are different physical quantities. Further, one of them is scalar energy and another one is a vector torque. This means that the dimensionally same physical quantities need not to be the same physical quantities. Dimensional formulas are given. Some of the dimensional formulas are as follows in the chart. Physical quantity is area and expression is length into breadth, and dimension formula is L square. Dimensional quantities, dimensionless quantities, and principle of homogeneity. On the basis of dimension, we can classify quantities into 4 categories: dimensional variables, dimensionless variables, dimensional constant, dimensionless constant. Now we are going to see about dimensional variables. Physical quantities which possess dimensions and have variable values are called dimensional variables. Examples are length, velocity, and acceleration, etc. Dimensionless variables. Physical quantities which have no dimension. Dimensionless variables. Physical quantities which have no dimensions but have variable values are called dimensionless variables. For example, specific gravity, strain, refractive index, etc. Third was dimensional constant. Physical quantities which possess the dimensions and have constant values are called dimensional constants. For example, gravitational constant, Planck's constant, etc. And fourth was dimensionless constant. Quantities which have constant values and also have no dimensions are called dimensionless constant. Example, pi e, Euler's number, numbers, etc. Principle of homogeneity of dimensions. The principle of homogeneity of dimensions states that the dimensions of all the terms in a physical expression should be the same. For example, if the physical expression for v square is equal to u square plus 2as, the dimensions of v square and u square are 2 as are the same as equal to L power 2 t power minus 2. Application and limitation of the method of dimensional analysis. This method is used to convert a physical quantity from one system of unit to another. Check the dimensional corrections of a given physical equation. Establish relation among various physical quantities. To convert a physical quantity from one system of units to another, this is based on the fact that the product of the numerical values n and its corresponding unit u is a constant. So that is n u is equal to constant or n1 u1 is equal to n2 u2. Consider a physical quantity which has dimension a in mass, b in length, c in time. If the fundamental units in one system are m1, l1 and t1 and other systems are m2, l2 and t2 respectively, then we can write n1 into m1, l1, t1c is equal to n2 into m2a, l2b, t2c. We have thus converted the numerical value of physical quantities from one system of unit into the other systems. 2. Check the dimensional corrections of given physical quantities. Let us take the equation of motion v is equal to u plus at. Apply the dimensional formula on both sides. Dimensional formula for v is Lt power minus 1 and u for Lt power minus 1 and a for lt power minus 2 and t for capital T. So let me get lt minus 1 is equal to lt minus 1 plus lt minus 1. Quantities of same dimension only can be added. We see that the dimensions of both sides are same, hence the equation is dimensionally correct. 3. To establish the relation among various physical quantities, if the physical quantity q depends upon the quantities q1, q2 and q3, that is q is proportional to q1, q2 and q3, then q is proportional to q1a, q2b, q3c. Q is equal to k is a proportionality constant. K is dimensionless constant. So q1a, q2b and q3c, where k is the dimensionless constant. When the dimensional formula of q1, q2, q3 are substituted, then according to the principle of homogeneity, the power of mlt are made equal on both sides of the equation. From this we get the value of a, b and c. Limitations of dimensional analysis. This method gives no information about the dimensionless constant in the formula, like 1, 2 up to pi is Euler's number, etc. This method cannot decide whether the given quantity is a vector or a scalar. This method is not suitable to derive relations involving trigonometric, experimental and logarithmic functions. It cannot be applied to an equation involving more than 3 physical quantities. And the fifth and final one is, it can only check on whether a physical relation is dimensionally correct, but not the correctness of the relation. For example, using dimensional analysis, s is equal to ut plus 1 by 3 at square is dimensionally correct whether the correct relation is s is equal to ut plus 1 by 2 at square.